Hi, welcome back. In this video, we are working on using the discrete-time Fourier transform properties. And this example that I'm going to give you here is one of my favorite examples in signal processing. This is a way of leveraging the periodicity property, to take a low-pass filter and convert it into a high-pass filter. Now, I want to remind you that in discrete time, a low frequency, and we've talked about this before, but I'm just reminding you, low frequency is like 0, right? Omega is equal to 0, plus or minus 2 pi, plus or minus 4 pi. These are low frequencies. Okay? And high frequencies, then what about high frequencies? Well, in discrete time, high frequencies are considered plus or minus pi, plus or minus 3 pi, plus or minus 5 pi. These are the highest of frequencies. Okay, so we're going to keep that in mind. And something that we can do in discrete time that we cannot do in continuous time is use the code, or use the we're not even going to get to the code, but use the low-pass filter to make a high-pass filter. It's kind of amazing, actually. So let's say that we have a high-pass filter. Maybe we've already coded it, right, because this is discrete time. And we're going to call this capital H LP for low-pass, e to the j omega. I'm using capital H here because it's a filter. It's the frequency response of a system. And remember that the ideal low-pass filter is 1 around low frequencies. So we'll say less than some cutoff frequency, where omega c is a constant and it's a parameter called the cutoff frequency. 0 else. Right? And this is over one period. Remember, the frequency response, or any Fourier transform of a discrete time system or signal, the Fourier transform is periodic with period 2 pi. So this is just over one period. Okay? This is what an ideal low-pass filter looks like. So let's just plot this, make sure that we're all on the same page, what it is that we're talking about. So we have omega here, and when the absolute value of omega is less than some parameter, then we have 1 is our frequency response. So something like this. Here's omega c, right? Minus omega c. So when the absolute value is less than omega c, we have 1, and we have 0 else, but that's only up to pi and minus pi. Then it has to repeat, right? It has to repeat at 2 pi. So, and remember, 2 pi is a low frequency. Minus 2 pi is a low frequency. So, and frequencies differing by multiples of 2 pi are identical. So if it lets through the 0 frequency, then it has to let through the 2 pi frequency, and so on. So this is an ideal low-pass filter. Now, the cool thing is, the really ingenious thing here is that if you shift this, in frequency, so if you take h of LP and you shift it by pi, we'll say to the right, although it doesn't matter. Let's identify what we have here now. So if I shift this by pi, then, so imagine taking this plot and shifting it by pi. I've got, here's my origin, 0. I guess I should draw that in black. So I've got my origin there, and I shift everything by pi, so the thing that was centered around 0 is now centered around pi. Right? And then this guy, if I shifted it to the right, this thing is now centered around minus pi. Right, so this is a 1, this is a 1, and this continues on. This is periodic because these things were periodic. And so what is this? Well, this is letting frequencies around pi through the filter. So this is not a low-pass filter anymore. This is a high-pass filter. Right? So the idea is that once you have a low-pass filter coded, then you can just perform some sort of manipulation to make it a high-pass filter. So what is that manipulation? Well, if we take the inverse transform to get the impulse response, so we apply the frequency shift property. This is the frequency shift property listed in tables, right? So if we apply the frequency shift property, then, and this is the dual to the time shift property, we need to multiply by this e to the minus j pi n times the low pass impulse response. Okay, so we've got this thing, and remember e to the minus j pi n is minus 1 to the n HLP there. So how did we get that again? Well, look, so if I take the Fourier transform, this is capital H of the high pass e to the j omega is equal to, we apply the frequency shift property. So frequency shift property says that if I multiply by a phasor in time, then I shift the frequency. So I'm multiplying by this pi, so I shift the frequency by pi, and so I get back what I had here. So again, the idea is that if you have a low-pass filter already coded, or this guy maybe, then all you do is you multiply it in your programming language by minus 1 to the n, and now you have a high-pass filter. And again, that has the effect of taking your low-pass filter in frequency and just shifting it up by pi. Pretty neat.